Morning. Over to you then, Chris.
Okay, let me get my screen shared. Hopefully that everybody see it. I'm on the web. I'm on the browser of Zoom, so it's doesn't quite tell me if things are sharing properly. So
See it perfectly. Thank you.
awesome. Okay, so let me set my timer here. So thank you everybody for showing up tonight. My name is Chris Tankersley. Um, I've been a part of the PHP community for a very long time, but tonight I'm not really going to spend a whole lot of time talking about PHP. I'm actually going to talk about Git. Uh, I was recently at the Longhorn PHP conference, and we kind of got into a discussion over a lot of developers nowadays are using some sort of version control, which is great. Um, and Git obviously has exploded over the last couple of years as well. But when we kind of get down to it, most developers tend to use like the 4 or 5 commands they know to like make a branch, push a PR up, and kind of go from there, without kind of really understanding what exactly you can do with Git, and exactly how it's actually doing all of these powerful things. So that's kind of what's bloomed out of this talk, is to give everybody a little bit better understanding of what Git is doing under the hood, which can help you understand what happens when it does go completely belly up, but also some of the more advanced things that you can do with Git as well as you start to use it more throughout the day, and some of the more powerful things you can do to kind of help keep things clean in your as you're developing. So one of my favorite quotes from a completely and utterly fictional character is that the greatest form of magic is not love or friendship, but chronomancy. Because if you can manipulate time, you can do whatever you want. And the beauty of Git is that it is literally just a timeline of events, and that's it. So because it's just a literal timeline, you can do a whole lot by going back and actually manipulating time and manipulating what your code looks like at any point in that timeline, once you understand how Git works and what you can do to actually jump back and forth, move around, all that kind of stuff. But at its heart, Git is just a timeline of events, and each of those events is each commit you make. So if we take a look at just like a Git log, and you'll see these hashes all over the place, just kind of ignore them. We're just using them as kind of labels. But if we look at a Git timeline, it's just this: we start at F8, and then we'll commit something. We'll get a hash called CFE, and then this just continues to happen all the way through as we work day to day. But if you go to look at Git, its log is just a timeline. Now, the way this actually is working is that Git stores snapshots of your files as well as keeping track of all of their parents. Now, one common misconception with Git is that uh, because you look at, especially like a diff interface, most of the time, like when you go look at a PR, you're looking at a diff between a couple files, 10 files, whatever. Git doesn't actually keep diffs of anything. Git actually takes, when you do a commit, it takes a full snapshot of everything in your repository as it stands at that time. It does some things to mark like this specific file changed or this specific file didn't change, but essentially it's taking a copy of the actual repository at that time. It's not doing something like actually like generating a diff and storing the diff off and like recompiling stuff, because that would actually be really, really time intensive. And the other kind of common misconception with Git is you actually need the entire history to do that. Uh, if it relied on diffs, you'd have to always check out everything. But Git, you could actually just check out the most recent snapshot, the most recent revision, and be able to work as if you could do whatever you want. You just can't go back any further in time. But because we keep a full snapshot of everything, including what each of the parents up the chain look like. So if we look at this again, D6E has every single file, a copy of that. 5AA, there's a copy of everything in there. Um, so that allows us to actually go through and jump back and forth in time. Yes, Git is not a Git is not a blockchain, but not for the reasons, the massive computational reasons. One of the most common things we can do with Git is actually just go back in time, and this is really useful if you're trying to figure out like when something broke or what something looked like, before a change was made. So if we go back to our timeline, the simplest thing we can do is literally just check out a period in the past. So when you do something like git checkout CFE88CD, all it's doing is rolling the pointer of time back to that specific point. By just doing the checkout, it doesn't delete anything. So those other three commits still exist. You're just rolling back in time. So basically, all the pointer where you're looking at just kind of shifts back to that set of files, and then you can start to manipulate them as much as you want. One of the most common things with Git is to create parallel timelines, um, which we would call branches. But you can use going back in time, fixing things, manipulating them, uh, you know, just kind of through the normal checkout process. So if we know that there's something that needed to be fixed back at CFE, we can do a git checkout. Uh, and here I'm just doing a dash B for a new branch name. And this creates an alternate timeline. So we don't do anything by disturbing the existing timeline. So CFE still technically flows through to 2CA, and the new commit, the new branch that we start with C40, that starts another branch. But basically, you can run multiple copies of these. And the way this all works is because everything is a full snapshot, it's super easy for Git to keep track of, for Git to keep track of where everything is going. Because really, when you look at it, a parent can spawn multiple children, but a child only has one parent. Now, if we're looking at this, and technically all of the pictures that I have in this talk are fundamentally wrong when we start to talk about Git. Uh, because I can't really see my screen, I'll ask this question and then answer it. Um, there is one thing wrong with all of these images that I've been doing thus far and throughout the rest. That's the order of these arrows. Git also does not look at things from a parent-child perspective. It looks at it from a child-parent perspective. So no matter what you're doing, when you look at something and you're looking at a log or Git's trying to figure out like how far back it needs to go for things, it takes a look at where you're currently at and then goes back up the chain. So if we're currently at 906, Git is actually storing it as 906. Its parent is C40. C40 parent is CFE. And that's how we can have multiple children to a single parent. But Git actually works reverse from the way we mostly think about it. I'll keep the arrows pointed this way just because fundamentally, when we think about things moving forward and time moving forward, we think of going from the oldest to the newest. But Git actually works in the reverse. It looks at the newest thing and then goes back as far as it can. Because really it's a child-parent relationship, not a parent-child relationship. The other thing we do quite commonly is combine timelines. So once we've branched off, many times we're going to need to merge those in. That's what a lot of times a pull request looks like. So for Git, this is what that actually looks like. From we branched off at CFE, the rest of the timeline continued up. So that's probably, the bottom straight line is our main branch. C40, we do some work. 906, we do some work. And whenever we get ready to put that all together, we will get, usually if you look at the log, is what's called a merge commit. And that's where we create basically just a pointer to say, hey, after D6E, we're going to take and put 906 after that. But the pointer for that is actually 91C. So 91C takes everything from 906, everything from D6E, puts those two sets of files together, and assuming that there are no conflicts, it's able to just merge that as a brand new merge. So this is a little bit different than all the rest of the commits because this is basically a thing with like two little pointers. Um, There's another type of merge called a fast forward merge. Those, especially with the way GitHub works, are generally less common. But those would actually take those two commits at the top and just shove them at the end if everything kind of works cleanly. And then you would actually, it'd be a lot harder to actually see that there was a branch. But most of the time, when you look at a Git history, especially if you're using GitHub or Bitbucket or any of the normal kind of like GUI tools, you'll end up with this kind of merge commit that is a pointer to basically two parents. Now, where we start to get kind of funky is when you have multiple branches or multiple timelines and you want to keep all that stuff clean, because a lot of us are not working on just a single, like we're not the only programmer in a group. There may be two, there may be three. You may be working with contractors as they're committing code. Uh, but one thing that ends up happening is with Git especially, you're keeping track of all of the histories you know about. Every other copy of the repository is a full copy of the repository, but it's looking at it through the lens of that specific person's checkout. One of the powerful things about Git is that, kind of at a fundamental level, everybody has a full history of the repository, and it is fully separate from everybody else's. This is a little bit different than older ones like SVN and CVS. And I know SVN's changed a lot how it's worked recently, so it's a lot more Git-like now. But if you look at older versions of SVN and CVS and RVS, they tend to be very centralized. So you have a central repository, and that is where all of the information is stored. You work against that copy. But even in a GitHub workflow where you do have a centralized copy up on the GitHub servers, Git still pulls everything down to you, and you look at it from your lens. So one of the things Git has to do is actually resolve multiple sets of timelines and make sure it actually looks all correct when you push it all up. So if we have a checkout on someone else's machine, this may be what their history looks like. So they branched at A9C, that made a branch at A7E, and then they merged that in. So you can see the log up there too, a little bit cleaner to look at. But they've got this kind of nice in and out. But the thing is, they're working on their branch. So they're doing some branch called feature slash time feature. They're adding some new stuff to that. They're working on their own thing. But on their machine, it looks just like this. But on my machine, I'm working with fixing some dependencies. So my branches, while they look fairly similar, are different. We both started at A9C, but when I branched, I got a completely different commit hash. When I merged, I got a completely different commit hash because I'm working on something differently. But from a visual aspect, they kind of look the same. So what Git actually has to be able to do is make all of this stuff work, because my repository looks different than someone else's repository, whether it's GitHub, whether it's a coworker, whatever. Git actually has to be able to take both sets of these kind of like working groups and merge them together. So I've got the remote, I've got the local there. Um, how it actually does that kind of depends on which gets pushed up first. So what we will say is, let's say I want to pull in those remote changes. So let's say the remote repository is actually GitHub. So my coworker pushed their stuff up. So that's what the Git resolved itself, and it's going to look like their remote repository. When I do a Git pull, Git actually does some stuff like this. So if I've merged my stuff into main and I Git pull down what GitHub says, we end up with this kind of, we both branch out at the same time, but my coworker comes in first and then I kind of come in after, just based on the fact that they merged probably before I did. But you get these kind of like funky ins and outs as it tries to resolve. And there's nothing really wrong with this in any sense of the matter. Git resolve this as long as there's no conflict, so we didn't accidentally overwrite someone's code. Git by itself will just handle this, no problem. Just kind of looks a little bit funky. What some people will recommend doing is a Git pull with a rebase flag. this is actually my preferred way of doing it, especially against like a main branch or a branch that I'm sharing with other people. Um, but what a rebase does is it alters the times of when it's assumed that you made your commits. So if we take the exact same setup, coworker merged before I did, with a rebase, what it will do is it'll take my master or my main branch, it'll reset that to whatever GitHub's is. So we have A9 branches to A7, goes back down to 244. And then the rebase will actually take all of my changes from my branch and move them after that. And you end up with kind of a cleaner in, like we have an out back into an in, and then an out back into an in. So it kind of flows up and down, or like depending on how your uh, grapher may do it, you may do like it may do humps, but you end up with this kind of a little bit cleaner in and out kind of status, and you don't end up with things looking like they happen at exactly the same time. But a rebase kind of redoes it a little bit differently. It's just shuffling around those change sets. Uh, this can be a little bit scary because you are changing time, and this is where you start to get into some of those things where uh, you know you've probably heard the mantra of don't use rebase, you'll lose code, or don't use rebase, you'll just get in, you're getting into these horrible monstrous waters. But all you're trying to do is figure out what's the best way to handle any sort of like time paradoxes that may occur. In my mind, I like the rebase a little bit better, especially with um, shared branches, especially like main, um, because in all honesty, and this is going to be a prevalent theme throughout the talk, a clean and easily readable history is much more preferable to a quote unquote accurate one. So this kind of jumbled mess of who branched when and what the timestamps and stuff are is technically the most accurate way of describing the work that was done. We both branched at A9. We both did our two branch works at roughly the same time, and they came in one after the other. But realistically, at the end of the day, I don't really care when a commit was made specifically, like an actual like timestamp. I care more about the order in which it was put into place. So that's why I kind of like doing the rebase way. So that way we kind of get this in and out a little bit better. Um, Especially when I'm doing a lot of stuff with teams, I don't care if you committed at 2 a.m. or 2 p.m. I don't care what day it is. As long as it got done by the deadline, that's all that matters to me. But if I need to go back and I need to reread this history, I'd rather have something that's nice and clean to look at where I can see a much more linear progression instead of having to have all of these things kind of coming in at exactly the same time. So that also gets us into our first kind of idea of rewriting history itself. Because whenever we do anything in Git, we are going to be rewriting some sort of history. Be it we're rewriting history as it kind of happens at the tail end, or we're going back and rewriting history to clean things up. One thing I really like to get, especially new developers, in the habit of is cleaning up after yourself, because history is written by the victors, and that's why there's no typos in history. Everything is clean. There are no problems. Um, but one of my really big pet peeves with any sort of commit uh, history, especially like going through like pull requests and stuff like that, is seeing commit messages like fixed typo, moved class, updated README 4 or 5 times in a row as you go through and do documentation. I don't care about those things. What I care about is when, what work was done, but I don't care about necessarily the steps you take to get there. What I care about is there a commit with a feature that needed to be added, or a commit with a bug fix that needed to be done. So if we take a sample history, let's say this is our branch that we're working on. I'm sure everybody can relate to a PR that looks like this. I added a feature, but then I realized as I added that feature, I ran the unit test after I committed, so I got to fix the variable name. So I fixed that. Then I go through, all the backend code's working, so I got to update the template. And then I fixed a typo I noticed on the page, but then I fixed another typo, and then we finally said it was done. I pushed it up. Realistically, I don't care that you typoed. Um, all I care about is that that new feature got added and the template got updated and that we're ready to go ahead and merge it. So I heavily recommend and suggest getting in the habit of cleaning up before you push up pull requests. Um, all of these kind of like commit quickly is really super useful when you're working locally and you might need to roll back because you're not sure about what you're doing or anything like that, or you want to make sure you're keeping a snapshot so you can easily roll back if something does blow up. But once we get to the PR stage, I don't care about all those interstitial steps. So this is where we get into rebasing. And again, you'll probably hear all the time, don't ever rebase. Rebase will cause you nothing but heartache. But really, once you understand what rebasing does, you kind of understand why things blow up sometimes. So to do a rebase, what you want to do is you want to find a commit before any of your changes and then rebase off of that. So here we're going to do a get rebase dash I C23D, which is actually the first length of our rebase. So what it will do is it will take that as the starting point of our rebase. And then anything after that is probably where we're going to make those changes. So the rebase starts before we actually did our first commit in our branch. So this could be, this is the commit you probably branched off of or whatever. But you always want to say, I want to manipulate stuff up, in this range, go one back further from that. So most of the time, and I'm going to be doing this from the basis of the command line because different GUIs do it differently. But what you'll get is a list of commits from that rebase hash you started with all the way up through the end of that commit line. So you'll see a file, like if you're looking at it for the command line, you'll see like pick each of the hashes and then a log of what each of those things were. So this is basically 3 columns. The first column where it says pick here right now is an action. This is what you're going to do during the rebase. And we'll go over what those different actions are here in a second. The second is a list of hashes, and these are the hashes we're going to manipulate. So you can look at this real quick and see if they look like they're the correct ones or not. And then everything else after that hash is the short description of what you committed. So we can see last important thing we did, new feature, all that kind of stuff. Now, the main actions you'll take during a rebase are pick. This says picking a commit basically says just use the commit as is. We're not going to alter it in any way. Just keep it. We're not going to do anything else with it. Reword lets you change the commit message. So your files will still contain whatever changes you made, but it allows you to edit the commit message. This is really useful if you're rolling up a bunch of commits into one and you want to just change that initial commit message to something much more cleaner, or you notice you misspelled the commit message itself, or you need to add an issue number, you can go back, reword it. So you won't change the contents, just that message. Edit lets you use the commit, but will stop at that hash and lets you actually change the files. This is sometimes where you can get into a little bit of a weird situation where if you edit something that gets edited later, that can cause problems. But basically, if you realize I forgot to do something, but I should have done it at a specific point, I can edit that hash, throw that change in there real quick, and go on from there. The last two are ways to take two sets of commits and merge them together. Squash takes the commit and copies all of those files into the previous commit, basically, but keeps track of the commit message. Fix up is the same thing, but it discards the log message. So the difference between squash and fix up is whether you just want to keep the comment, or just keep all the comments, or just the first comment. Squashes I tend to use when merging pull requests, because I want a full feature or a full bug fix to be just a single commit, even if it was 5 or 6 different blocks of work. I'll usually squash that down into one, but I want to keep track of everything we did during that. But fix ups I tend to use day to day to do like those typo cleanups and stuff like that before I push up for a PR. So I don't care about the fixed typo messages and stuff like that. We'll just roll all of those up. If you go back and look at these slides later, just keep in mind squashing is best for merges, I think. Fix up is better for day-to-day cleanup. So what actually happens once we start that rebase? So we did get rebase -I, it starts to kick off and it's going to start going through all of these things. The first thing we want to do is in that commit message that it brings up with pick and all that, we want to tell it what to do. So in this case, we're going to do some fix ups because, like I said, fix up is better for day-to-day stuff where I don't care about messages. So we're going to fix up 3 lines: the 3rd line, the 5th line, and the 6th line. So we're going to take those things and kind of roll them back up. So once we kick off the actual rebase, it's going to create a new document set with all the combined texts of 1B and 2.1. So we picked C2.3. We just use that. Nothing changes there. So we can just say we roll on to the next one. Technically 1BA we picked. We're not going to change that at all. It sticks there. When we hit fix up, it's going to say, okay, take everything in 2.1.4, merge that with everything in 1BA. So it's going to create a whole new document set. What usually trips people up at this point, especially if they're keeping track of hashes, is that hash changes. Now, the reason for that is because technically we have created a new set of documents. 1BA and 2.1.4 were 2 discrete units of work. When we put them together, that's a whole new unit of work that we created. So it gets a brand new hash. It's a new set of documents. So all of a sudden that commit changes to 8ED. Now, if we're just doing a rebase, most of the time you're probably not caring about the hashes, but this is important to keep track of because if you're looking at, someone else's history and they have a copy of your branch before you merged it, a lot of these hashes are not going to look the same because basically from this point, we're starting to rewrite history. So we take those 2 document sets, merge them together, and then essentially that gets picked. We're going to keep that from that point forward. And then we pick A9C. We don't do anything to it, but then we hit A7. It's going to do the same thing. It's going to take all of those, everything in A7, copy them and merge them into A9. And then even though we're going to do 2 fix ups, that resolves atomically. So we get a whole brand new commit with that new document set. So we get 3D5 out of that one. Then we go on to the next step, fix up for 2.4.4. We're going to roll that back into what is now 3D5. That generates a whole new document set. We get a whole new hash again. And then because all of these file sets have changed, the bottom one will also change because now it includes all of the things we've rolled up there. So what the rebase is doing is just, in this case, it's taking those things, squishing them together into the most important things. And probably the most important thing is no one knows I made any typos when I was doing all of my work. I just did all of the perfect work and no one is the wiser. But if we turn around and we look at the git log from that point on, it'll look like this. It's the nice condensed down version. It's all brand new hashes. I can push this up. If anybody's looking at the individual commits, especially if you're trying to, like, you've got, you push the commit up and then so you push something up later, they can look at the individual commits. They'll be much more complete. They won't have all that extra junk in there. One thing I will warn with rebasing, because it is very dangerous because you are manipulating history, rebase as much as you want on your own personal branches. So generally, like when I schedule workout, individual like tickets at work, I try to make sure no one else, like each person kind of has their own thing to work on. They're not stepping on each other's toes. Usually it's not until we get to kind of like big integration stuff where we've got 3 or 4 people working on an individual feature branch. But whatever branch you're working on yourself, rebase as much as you want out of that. You're not going to harm anything. We'll show in a second where you can actually pull stuff back out. But you can rebase your branches as much as you want and then force push to your own personal branches as much as you want. Where you start to run into problems is when you have multiple people working on that same branch. So if you rebase which is going to necessitate a force push up. Other people have to do other work to actually fix it so that they're looking at what is the new kind of like history. So what I generally try to say is rebase on your own personal branches, but not on anything shared. So don't ever rebase your main branch. Fix it properly via pull requests, but don't ever go through and rebase main or dev or anything where you've got a lot of people coming into the same space. Now that being said, there is a chance you can lose code if you hit a merge a conflict when it's doing those kind of fix ups and trying to like wind stuff back together. You could mess up doing a commit. You could accidentally lose code. But the cool thing about Git is it doesn't forget where anything is. So nobody forgets where they buried the old commits. There's a slight caveat with that. Git will forget where old commits were after a certain period of time. By default, it's 90 days, which is usually enough. But because Git is keeping full copies of every single set of commits that you do, that wastes a lot of hard drive space. So it does do some garbage collection over time. But if you catch a screw up quick enough, you can go back and retrieve old code within about 90 days. So when we did our rebase, what actually happened was we created another timeline. It's essentially another branch. If we look at the mainline history, we get the nice straight one at the bottom. We get where we started our rebase and our 3 rebased and brand new hashes as part of that. But we didn't actually alter the original commits that we made. So if we did actually need to go through and go back and be like, like I swear this worked before I did the rebase. Let me look at, the old system. There is a thing called a ref log, which I'm not going to get too deep into the weeds. It's because there's a lot of stuff you can really do with it. But through the Git ref log, you can actually go back and look at every single commit that has happened in your local repository. And I will stress that as your local repository. The ref log is a singular record of everything you have done, but it does not necessarily contain anything anyone remote has done unless you've pulled their stuff down either through GitHub or stuff like that. So let's say there was something important that I put in an A9C at that top branch, and I really got to go back to that and pull that back out. I can actually do a git checkout back to that hash, even though in the history it doesn't technically exist. It still exists in the ref log. You can always look at your ref log to pull that kind of stuff back out. Because essentially all Git's doing is just changing the parent. So when we started doing that rebase, we basically just changed the parent of 8ed and pointed it back. And since everything is child parent related, we don't see that extra set of commits that we'd had before, even though Git actually knows they're still there because they're still in that big giant list of stuff you did. But that also brings up another important part of manipulating time. So if you're familiar with time travel and all that stuff, this is all parallel time travel. Technically, when you go back, you're splitting the timeline again. You're never altering anything that's already happened. But let's say you really, really need to kill your grandpa for some reason. There are ways to go back and completely clean up history. It's still not as foolproof as people would like to perceive, but let's say you want to actually completely get rid of something from the ref log, everything else. There is another Git tool called filter branch, which is extremely complicated to use, especially to just remove files completely from history. There is a better tool called the BFG repo cleaner. But what Git filter branch and BFG are designed to do are they actually go through the ref log and actually delete stuff from the ref log so that they are completely and utterly gone. Most of the time, BFG will be recommended if you accidentally do something like you commit an SSH key or you commit your AWS credentials or whatever to a repository. Someone will say use BFG repo cleaner or filter branch to delete those credentials from your repository. Because basically what you'll do is you'll run BFG on your local repository, it'll do all of its cleanup, and you'll do a force push up to kind of like say like, nope, my history is the correct one, get rid of everything else. The one downside that sometimes gets overlooked, I just realized I have a typo in there. BFG repo cleaner only affects your local branch and only specifically what you force pushed to. What is really common is you accidentally commit, let's say, your AWS credentials. You may not notice for a couple hours. You may not notice for a couple of days. Even if you run repo cleaner on your stuff, let's say after a couple of hours, and you push that up and you force push that up to GitHub or whatever, anybody who checked out your repository in those intervening couple hours will still have a copy of your keys. They are under no obligation to make sure that their repository is completely cleaned up. So even if you delete those keys and stuff, you will still want to rotate any passwords that were in there, any keys, whatever, because you don't know how many copies were made in that time span before you noticed and before you ran repo cleaner. It fixes the problem going forward, but it doesn't fix the problem in that intervening time. So I would just keep in mind that if you are completely deleting stuff from the ref log, you'll still want to rotate any of those things. It's not a run repo cleaner and now all of a sudden you're good. One common thing we do is pulling in changes from the main timeline, especially over time. Now this is a little bit different than, I'm just pulling in main or to just update it locally. But a lot of times if you have a very long running branch, there are times where bug fixes will get made that you need to pull into your branch because you discover that's affecting either your ability to do the main timeline or to do your feature fix, or you're running into a situation where uh, it's affecting your ability to do your work. So you need to pull in changes from your timeline, but you're not to the point where you actually need to uh, actually commit your code. So let's say we've got a couple branches here. We branched off, we've got our branch running. What a lot of people will do is this. So we're in our branch currently. They'll fetch origin, which will be like GitHub or whatever, and then they'll merge in main into their branch. So you'll get kind of this. So 45E, that is a merge commit. That's one of those funky little commits that says basically I'm taking two things and combining them. But you'll do this over and over and over. And especially if you have a really long running branch, you will get these things where you're just interstitially shoving main up into there. And if you're doing that a lot, it can get kind of ugly. But again, too, you're kind of, it's one of those things that could reduce merge conflicts, but it can also cause merge conflicts later on, too. The alternative to this is doing another rebase. This is a kind of like a merge rebase. So instead of doing a git merge origin main, you can rebase off of your origin main. Functionally, this should do relatively the same thing. But because rebases change the order in which things happen, what you end up with is it takes all of your commits, moves them to the side, moves everything to the current version of main, and then layers all of your commits back on top of main after that point. So if you actually look at the log, we go from this, we branched at CFE, had a couple commits, and then had the merge commit. Instead of branching off CFE, we actually now branch off 5AA, which is, whatever the last thing in main was. This is another one of those where I prefer this, especially because it tends to be cleaner. Because again, all of these changes, I don't care when they happen. I just want them to be easy to follow backwards if I need to. This will have as much chance to have merge conflicts as doing the other one. And this is usually where people will run into issues. Both doing merge commits from main and doing a rebase from main is really useful if you do them often. If you do them every 3 weeks, every 4 weeks or whatever, because you've got a really long feature you're working on, you're going to run into merge conflicts either way. Neither the rebase is probably cleaner to resolve from, because if you run into a whole bunch of them, you can stop the rebase and roll back to where you were. If the merge comes in, it can be a little bit ugly to clean up and roll those back too. But neither of these things are necessarily going to save you from merge conflicts. Merge conflicts will happen no matter what when two people work on the same file, or I'll say they increase when two people work on the same file. Uh, the act of rebasing does not necessarily increase the chance of a conflict happening. All of that is basically due to uh, multiple people working on the same files. So the only real fix for that is to make sure that when issues are created or features are being worked on, everybody kind of gets sandboxed to their own little section of the code base. Now, the last thing, and probably one of the most important things that you'll probably do with Git and bug fixing, is actually playing detective. So because we can jump around in Git, and because Git keeps track of files as they are, we can actually jump around to try to find when bugs got introduced. So this is done with a tool called Git bisect. You can do this completely by hand, because all bisect does is it's just an automated tool to jump you around the timeline, not necessarily to do anything special. But what it will do is it'll basically take a start and stop and then jump around till you can find a bug. So let's say you found a bug in the latest version of the code, but you're not sure when it got introduced or like how a change got made. And you want to figure out, like I know it used to work, what exactly happened. And this can be done before you actually look at the code, so you can kind of like narrow some things down. But what you want to have is two things. One is going to be when the bug was discovered. The second is going to be a good commit. So we know that the bug exists at B2B, and we know that it worked at C23. So we're going to use those two things because Git bisect needs a good commit and a bad commit. Sorry, we know that it worked at 1BA. So we have our bad one, B2B. We have our good one, 1BA. Running Git bisect is actually pretty easy. You just say Git bisect start. That if you don't give it a hash, it'll use wherever you're currently at. So if we're already on B2B, we don't have to give it, but you could give that if you wanted it to. And then you just give it Git bisect good, the starting point, and then it'll start to jump around. So it'll start us where we start to begin with. We look at that and you just say this commit is bad. So you say Git bisect bad B2B because we know that one's already bad. So it effectively says 1BA is good, 2B2 is bad. When we run Git bisect bad, it'll jump us to the midpoint or as close to the midpoint in the history as possible. So Git bisect will also, when we do a bad, move us to another commit. So now we're on A9. We can look at that, run unit tests, we can run integration tests, whatever. We're going to say that one's still bad. So we say Git bisect bad. That marks A9C as bad, jumps us back to 214 because that's the midpoint between the last good and our newest known bad. And then we can test that. We will never have to go through and check A7 or 24 because we know A9 is bad. There's no point in actually going back and checking those. Git bisect will never send us to that half of the timeline. So it starts to narrow down the timeline to see where it's good. And you're going to keep doing Git bisect bad until you find one that's good. So let's say 214 is actually good. We can say Git bisect good. Then through a process of elimination, Git will turn around and when you're all finished, say A9C is probably the first bad commit. So you know that you can jump back to that history, look at that commit, see exactly what happened, and fix things from there. When you're all good, you just say Git bisect reset. It cleans everything up, puts you back to the end. Again, you can jump back to that point in history. You can take a look at that commit message, that diff, see what's going on, and kind of fix the bug from there. So there's a lot more you can do with Git 2. I think these are some of the more common things, and that you'll probably do day to day between the cleaning up typos and the Git bisect and all that. But also hopefully it gives you a better understanding of what exactly Git is doing under the hood. So with that, thank you very much. Again, my name is Chris Tankersley. I'm a lead engineer at smarTours, which is a travel company. and I've been a PHP Fig core community member for many years now. If you want, I do apologize, I'm gonna have to hop off to go get my kids here soon. But if you want to get with me after the fact, you can reach me on Twitter as @DragonManTank, or feel free to send me an email at chris@ctankersley.com, or you can check out my blog, which gets updated once or twice a year. But hopefully that gets you set on a good way with how Git works. And I got a couple minutes I can take some questions, but otherwise, thank you very much.
Thank you very much, Chris.
Thank you, Chris.
Thanks, Chris.
Thank you.